Okay, we're back to finish up our Newton's second law examples. Let's pick up with this one. A 25 kilogram object concurrently experiences two forces. The word concurrently means at the same time. Okay, so that's a new word for you. You probably haven't heard it before. It means at the same time. So at the same time, it's experiencing two forces. One force is 100 newtons and directed eastward, while the second force is also 100 newtons but directed westward. What is the acceleration of the object? Okay, so you might be thinking, okay, I'm pretty sure I know the answer to this, but it's not something we can just assume. You have to show the work for how you know what the answer is. We're looking for the acceleration, we're told the mass, and we're given two forces. One force is directed to the east, one force is directed to the west. I'm going to call the eastward force just maybe F1, and I'll call the second one F2. Notice that we're not given the net force. If you're not given the net force, if you can't just simply plug into one equation and be done with it, then you really should be drawing a net force, a free body diagram, and writing net force equations. So that's what we're going to do. Here's our dot. I'm just going to label it object. Our axis, let's do the standard XY. And we have two forces on the object. We're not going to label anything like force of gravity or force from the ground or anything because we're just told, I mean, it could be that these two forces, well, I guess not, it can't be the force of gravity since it's west and east, but we're told that it's just two forces. Okay, so let's just go with that. Don't make things too complicated. We're told that one force is directed to the east, 100 newtons. We called that F1. The other force is directed to the west. We call that F2. If I'm scaling this, then my vectors need to be approximately the same size. Now, right after I've done the net force, the free body diagram, immediately afterwards, I write the net force equation. F net, and this is the x direction according to my drawing, equals, what are the forces in the positive x direction? That would be F1. And then forces in the negative x direction, F2. So that's minus F2. F1 minus F2 equals MAX. Notice that I'm putting an x here, even though there are no forces in the y direction. If you write F net x, then you should put a little x on your acceleration as well. So you should get in the habit of saying whether we're talking about the acceleration in the x direction or the y direction, and the net force in the x direction or the y direction. If you don't label this, then I might take off some points. Okay. Again, we're not looking for the net force in this case. We're looking for the acceleration. I don't know what the net force is, but I do know what F1 and F2 are. So I'm not even going to bother to continue writing the F net x part. I'm just going to plug in. I know F1 is 100 newtons, and I know F2 is also 100 newtons, and I know the mass is 25 kilograms. Now, at the beginning of this problem, you might have been like, why do we have to go through all this? We know that the forces are balanced. Again, you have to show the work. 100 minus 100 is 0, divided by 25. The acceleration, in this case, must be 0 meters per second squared. Okay? Even if you knew the acceleration was 0 at the beginning, you have to be able to provide written proof of why that is. Okay? Use math to do your reasoning for you. Now, what does this mean? Does this mean that the object is stationary? Not necessarily. It could be stationary. It could be not moving. It could have a velocity of 0. Or it could have a constant velocity. It could be moving, but just not accelerating. What does that mean? It means the velocity is constant. Third question. Two forces act in exactly opposite directions on a 10 kilogram object, which is accelerating at a rate of 3 meters per second squared. If the force that acts in the direction of the object's motion is 40 newtons, what is the magnitude of the force that acts in the opposite direction? Okay, so we have a kind of tricky problem here. We're given the mass, and this time we're also given the acceleration. And we're told that there are two forces. One force, I'm going to label again as F1, is 40 newtons, and we want the size of the force in the opposite direction. We're going to label that as F2. So I can't figure out what F2 is just based on this, just based on one equation. So I'm going to draw my free body diagram. Once again, here's our object. I have F1, and I have F2. I don't necessarily, I mean, I actually could imply the sizes of these forces before solving the problem, but I'm not going to in this case, so I'm not going to scale my diagram this time. Our net force equation in the x direction is, again, F1 minus F2 equals max. Now it comes time to start plugging in. I know the mass and I know the acceleration, so I can definitely plug in for those, so that part is useful to me. I know that the force that acts in the direction of the object's motion is 40 newtons. So let's make this easy on ourselves. Let's say that the object is moving to the right, and therefore it's also going to be accelerating to the right. Maybe I should have been more clear with this problem. That's not always going to be the case. Objects do not always move in the direction of their acceleration. That works. Objects do not always move in the direction of their acceleration. But in this case, let's take the simplest possible case. Okay, let's say that the force that acts in the direction of the object's acceleration is 40 newtons. So, since this object has a positive acceleration, and we said that positive was to the right, F1 is to the right, that must be the force that's 40 newtons. We want the force in the opposite direction, so we're solving for F2. Again, we're not solving for the net force this time. There might be problems where you do solve for the net force, but in this case, we're solving for F2, the force in the opposite direction. Again, I don't know what F net x is, but that doesn't even really matter. I have F1, I have m, and ax. I only need two parts of that equation, this part and this part, to solve for F2. Yeah, could I use the mass and the acceleration to find the net force in the x direction, and then use that net force and F1 to solve for F2? Yeah, but that's a whole extra step. You're doing more work than you have to. Look for the parts of the equation that you either fully know or that you're solving for, and just use those. So in this case, I don't need, it's important for me to write F net x at the beginning. I don't need it. I'm not going to continue writing it. So F1, we just said, was 40 newtons minus F2 equals the mass, 10 kilograms, times 3 meters per second squared. And I solve for F2. So I get 40 minus F2, I'm going to write this one out because it's a little tricky, equals 30. I want to solve for F2. So I need to get F2 alone by itself. There's a couple different ways I could do this. I could add F2 over to the other side and subtract 30 over to the other side. Or what I'm going to do in this case is I'm going to subtract 40 from both sides. That leaves me with negative F2 equals 30 minus 40, which is negative 10. Now that's not my answer. I need to solve for F2, not negative F2. I divide both sides by negative 1, and I get that F2 must be equal to 10 newtons. Okay? Now you might be saying, wait a second, it's in the negative direction. Why isn't it negative? When you solve for forces, they will usually come out to be positive, okay? The negative only means that it's in the negative x direction, okay? It doesn't mean anything specific about the force other than telling you the direction. So when we solve for just F2, what we're doing is we're solving for the magnitude of F2, the size of F2. That's what we're doing there, okay? So F2 equals 10 newtons, okay? So once again, we see that we can solve actually a pretty complex problem. We solved for the size of this force just based on knowing F1 and the mass and acceleration. The second to last problem here, this is one of the problems that's a little on the tougher side right now. As you see it more and more, you will get better and better at solving this type of problem. But right now, this is probably going to be a little tricky for you. A net force causes an object to accelerate. If that same net force acted on an object 3 times as massive, how would this acceleration compare to the original acceleration? There are 2 ways to solve this problem. Way number 1 is to make up some values. You're not given any numbers in this question. And I like to say, make up numbers that aren't 0, 1, and 2. Those can be misleading. You're not given any numbers in this question. So there's nothing that stops you from making up some numbers for you to use. Okay, you can totally make up numbers for you to use. So we know the net force is causing some object to accelerate. I know that the net force equation is F net equals m times a. Now, what I could do is make up some numbers that work. Let's choose some easy ones. Let's say if the mass is 3 and the acceleration is 4, let's see, is that going to work? Let me think about it, what would work well here. Okay, we're going to end up using the same net force. We want to have an object that makes whatever, it'll work. The net force, so let's say that the mass is 3 kilograms. Let's say that the acceleration is, I don't know, 6 meters per second squared. What would the net force be? Well, I know that 6 times 3 is 18 newtons, okay? So I made up some numbers that are internally consistent. They work, okay? If a mass of 3 kilograms has an acceleration of 6 meters per second squared, the net force on it must be 18 newtons. Now, it says if that same net force acted on an object 3 times as massive, well, how would the acceleration compare? So that would mean making that 18 Newton net force act on an object that's 3 times as massive as the original 3 kilogram object. 3 times 3 is 9. So that's like saying, have this act on a 9 kilogram object. What would the acceleration be? 18 divided by 9 is 2 meters per second squared. How does this compare to the original acceleration? Well, the original acceleration was 6 meters per second squared. The acceleration now is 2 meters per second squared. The answer then, how does it compare, is that it's 1/3 of the original. So, making up numbers is one way to do this. It's not the most elegant way, it's not the it's not the best solution, but it is something that works. The risks are, what if you accidentally make a mistake with your math? Okay, that could happen. There is a second way to do this, and it involves using algebra. Not that you weren't using algebra before, but it involves using algebra and not having to make up all these numbers and potentially get some math fact wrong. Let me show you what I mean. We know that F net equals m times a. Now, watch carefully. We know that it's going to be the same net force the second time. So I'm going to write F net, but it's a different mass. So I'm just going to put down here maybe m1 to denote that we're talking about something different from the original. Okay, originally we just had F net equals m times a. Now I'm going to have the same net force, F net equals m1, and that's probably going to change the acceleration. So I'm going to write a1. Now the key here is I need to be able to write m1, that's the change that I know about, in terms of the original m. The original m, well, let me back up. The new mass is now 3 times as big as the original mass. So if I want to relate m1 to m, the original, I would write this. m1 equals 3 times m. m1, the new mass, is 3 times the original mass. I'm going to plug that into this equation. F net equals 3m a1. All I did was I related the new mass to the old mass. The new mass is 3 times the old mass. And notice that F net, remember, that didn't change. I know that F net equals m times a. The original net force is equal to the original mass times the original acceleration. Well, look at this. I have F net in both of these equations. I'm going to take this F net and plug in what it was equal to. That would be m a. And I'm going to drop those parentheses just so this is really easy, equals 3m a1. Notice what I have on both sides here. I have an m. I'm going to cross off those m's, and I'm left with a equals 3a1. Again, I want to compare the new acceleration to the old acceleration. The new acceleration is a1, so I'm going to get a1 by itself. Watch what this does. If I divide both sides by 3, I get that a1 is equal to a over 3. The new acceleration is equal to the original acceleration divided by 3. Or, an equivalent way of saying that is the new acceleration is 1/3 of the original acceleration. New A is 1/3 of original. Now, at this point, I don't expect you to be able to do this by yourself. If you can follow this line of thinking, great. Okay, you might have to watch it and do it a couple times for it to really sink in. If you're still completely lost on what I was doing here, I do recommend going back and rewatching. But there's nothing wrong at this stage with making up numbers to solve like this. The point is, a question like this should not be a complete guess. There should be some sort of reasoning, some sort of written work involved in a question like this. You shouldn't just be blindly saying, the mass is 3 times as big, so the acceleration is 3 times as big. Matter of fact, that's wrong. Okay, that reasoning is wrong. So there should be some sort of work associated with questions like this. You're going to start seeing a few of those types of questions. Okay, again, we're going to practice this a lot more. Hopefully, one of these ways made sense to you. This way is fine. We are going to focus in this class on showing this way until hopefully everyone can get it by the end of the year. And you guys will, trust me. Last example, the net force on the car while it is uniformly accelerating is 450 newtons. If the 2,000 kilogram car accelerated for 15 seconds, what is its final velocity? So this is why we talk about forces in the first place. This is why we draw free body diagrams, why we write net force equations and solve for accelerations. Because once we know the acceleration, once we know how the velocity is changing, then we can predict things like how fast is it moving and where does it end up. So let's talk about what we know. The net force on a car is 450 newtons. That's net force. If the 2,000 kilogram car, that's the mass, accelerated for 15 seconds, that's the time, what is its final velocity, VF? And I should add, that it's uniformly accelerating from rest. In other words, VI is 0 meters per second. So look at all these variables. I haven't dealt with T, VF, and VI in a little bit, but they're going to end up being useful because once I know the acceleration, I can determine what I'm looking for, the final velocity in this case. This is a classic example of it might not be very obvious what to do from the beginning, but you gotta pick an equation that you can solve for something and then you just go with it. In this case, to solve for the final velocity, you might be like, okay, well I have the time and I have the initial velocity, but I don't have the acceleration. That's bad. Well, I can't use that equation. That's fine. Look at what else you have. You're told F net and you're told M. F net equals MA. Even if it's not very obvious why you might want to use this equation right now, use it, solve for the acceleration, and then just take a step back and see where you are. The net force is 450 newtons. The mass is 2,000 kilograms. And the acceleration, therefore, is the quotient of those two. 450 divided by 2,000, 0.225 meters per second squared. So there's the acceleration. Now, take a look at what we know. We're looking for the final velocity. We have the initial velocity of 0. We have the time, and now we have the acceleration. This means that now that we did that work in the beginning, we can use the Fiat equation, VF equals VI plus AT, to solve for V final. I know the initial velocity is 0. I know the acceleration now is 0.225 meters per second squared, and I know the time is 15 seconds. Therefore, I take the acceleration, multiply by the time, and I get a final velocity of 3.375 meters per second. Again, the entire reason that we go through all of the force stuff is so that eventually we can solve for the final velocity, or we can solve for the distance traveled. We write free body diagrams and net force equations so that we can predict where something is going to end up in a lot of cases. Okay? We are still studying motion. It's just that now, instead of being told the acceleration, we're being shown how to determine the acceleration. Okay, so that's how these two units kind of connect. That's everything I want to talk about with net force. If you have any questions, let me know. If not, then I will see you when we talk about weight and normal force next time. Bye.